In programming language theory, lazy evaluation, or called by need as an evaluation strategy which delays the evaluation of an expression until its value is needed and which also avoids repeated evaluations. The sharing can reduce the running time of certain functions by an exponential factor over other non-strict evaluation strategies, such as call by name. By contrast, there is no deferral with short-circuit evaluation where the result may be determined before all the expression has been evaluated, as in, should A evaluate to true there is no need to consider B. The benefits of lazy evaluation include, performance increases by avoiding needless calculations, and error conditions in evaluating compound expressions, the ability to construct potentially infinite data structures, the ability to define control flow as abstractions instead of primitives. Lazy evaluation is often combined with memoization, as described in John Bentley's Writing Efficient Programs. After a function's value is computed for the parameter or set of parameters, the result is stored in a lookup table that is indexed by the values of those parameters. The next time the function is called, the table is consulted to determine whether the result for that combination of parameter values is already available. If so, the stored result is simply returned. If not, the function is evaluated and another entry is added to the lookup table for reuse. Lazy evaluation can lead to reduction in memory footprint, since values are created when needed. However, lazy evaluation is difficult to combine with imperative features such as exception handling and input-output, because the order of operations becomes indeterminate. Lazy evaluation can introduce space leaks. The opposite of lazy evaluation is eager evaluation, sometimes known as strict evaluation. Eager evaluation is commonly the default behavior used in most programming languages. History: lazy evaluation was introduced for lambda calculus by Christopher Wadsworth and for programming languages independently by Peter Henderson and James H. Morris and Daniel P. Friedman and David S. Wise. Applications: delayed evaluation is used particularly in functional programming languages. When using delayed evaluation, an expression is not evaluated as soon as it gets bound to a variable, but when the evaluator is forced to produce the expression's value. That is, a statement such as x equals expression clearly calls for the expression to be evaluated and the result placed in x, but what actually is in x is irrelevant until there is a need for its value via a reference to x in some later expression whose evaluation could itself be deferred, though eventually the rapidly growing tree of dependencies would be pruned to produce some symbol rather than another for the outside world to see. Delayed evaluation has the advantage of being able to create calculable infinite lists without infinite loops or size matters interfering in computation. For example, one could create a function that creates an infinite list of Fibonacci numbers. The calculation of the nth Fibonacci number would be merely the extraction of that element from the infinite list, forcing the evaluation of only the first n members of the list. For example, in the Haskell programming language, the list of all Fibonacci numbers can be written as: in Haskell syntax, prepends an element to a list, tail returns a list without its first element, and zipwith uses a specified function to combine corresponding elements of two lists to produce a third. Provided the programmer is careful, only the values that are required to produce a particular result are evaluated. However, certain calculations may result in the program attempting to evaluate an infinite number of elements. For example, requesting the length of the list or trying to sum the elements of the list with a fold operation would result in the program either failing to terminate or running out of memory. Control structures: in many common eager languages, if statements evaluate in a lazy fashion. If and then else C. Evaluates, then if and only if evaluates to true does it evaluate, otherwise it evaluates. That is either or will not be evaluated. Conversely, in an eager language the expected behavior is that define f, x, y, equals 2x, set k equals f, d, e. Will still evaluate when computing the value of f, d, e, even though is unused in function f. However, user-defined control structures depend on exact syntax, so for example, define g, a, b, c, equals if at then BLC, L equals G, H, I, J, I, and would both be evaluated in an eager language. While in L equals if H then I else J, I, all would be evaluated, but never both. Lazy evaluation allows control structures to be defined normally, and not as primitives or compile-time techniques. If or have side effects or introduce runtime errors, the subtle differences between them can be complex. It is usually possible to introduce user-defined lazy control structures in eager languages as functions, though they may depart from the language's syntax for eager evaluation. Often the involved code bodies and need to be wrapped in a function value, so that they are executed only when called. Short-circuit evaluation of Boolean control structures is sometimes called lazy. Working with infinite data structures, many languages offer the notion of infinite data structures. These allow definitions of data to be given in terms of infinite ranges, or unending recursion, but the actual values are only computed when needed. Take for example this trivial program in Haskell. In the function number from infinite list, the value of infinity is an infinite range, but until an actual value is needed, the list is not evaluated, and even then it is only evaluated as needed. List of successes pattern. Other uses. In computer windowing systems, the painting of information to the screen is driven by expose events which drive the display code at the last possible moment. By doing this, windowing systems avoid computing unnecessary display content updates. Another example of laziness in modern computer systems is copy-on-write page allocation or demand paging, where memory is allocated only when a value stored in that memory is changed. Laziness can be useful for high-performance scenarios. An example is the Unix map function, which provides demand-driven loading of pages from disk, so that only those pages actually touched are loaded into memory, and unneeded memory is not allocated. MATLAB implements copy-on-edit, where arrays which are copied have their actual memory storage replicated only when their content is changed, possibly leading to an out-of-memory error when updating an element afterwards instead of during the copy operation. Implementation. Some programming languages delay evaluation of expressions by default, and some others provide functions or special syntax to delay evaluation. In Miranda and Haskell, evaluation of function arguments is delayed by default. In many other languages, evaluation can be delayed by explicitly suspending the computation using special syntax or, more generally, by wrapping the expression in a thunk. The object representing such an explicitly delayed evaluation is called a lazy future. Perl 6 uses lazy evaluation of lists, so one can assign infinite lists to variables and use them as arguments to functions, but unlike Haskell and Miranda, Perl 6 doesn't use lazy evaluation of arithmetic operators and functions by default. Laziness and eagerness. Controlling eagerness in lazy languages. In lazy programming languages such as Haskell, although the default is to evaluate expressions only when they are demanded, it is possible in some cases to make code more eager, or conversely, to make it more lazy again after it has been made more eager. This can be done by explicitly coding something which forces evaluation or avoiding such code. Strict evaluation usually implies eagerness, but they are technically different concepts. However, there is an optimization implemented in some compilers called strictness analysis, which, in some cases, allows the compiler to infer that a value will always be used. In such cases, this may render the programmer's choice of whether to force that particular value or not irrelevant, because strictness analysis will force strict evaluation. In Haskell, marking constructor fields strict means that their values will always be demanded immediately. The sec function can also be used to demand a value immediately and then pass it on, which is useful if a constructor field should generally be lazy. However, neither of these techniques implements recursive strictness. For that, a function called deepsec was invented. Also, pattern matching in Haskell 9.8 is strict by default, so the qualifier has to be used to make it lazy. Simulating laziness in eager languages. Python. In Python 2x the range function computes a list of integers. The entire list is stored in memory when the first assignment statement is evaluated, so this is an example of eager or immediate evaluation. In Python 3x, the range function returns a special range object which computes elements of the list on demand. Elements of the range object are only generated when they are needed as evaluated in the following example, so this is an example of lazy or deferred evaluation. This change to lazy evaluation saves execution time for large ranges which may never be fully referenced and memory usage for large ranges where only one or a few elements are needed at any time. From version 2.2 forward, Python manifests lazy evaluation by implementing iterators unlike tuple or list sequences. For instance, the above example shows that lists are evaluated when called, but in case of iterator, the first element 0 is printed when need arises. .NET Framework. In the .NET Framework it is possible to do lazy evaluation using the class system lazyT. The class can be easily exploited in F using the lazy keyword, while the force method will force the evaluation. There are also specialized collections like Microsoft FSHARP collection sec that provide built-in support for lazy evaluation. In C and VB.NET, the class system lazyT is directly used. Or with a more practical example. Another way is to use the yield keyword. See also, combinatory logic, currying, data flow, eager evaluation, functional programming, futures and promises, graph reduction, incremental computing. A related concept whereby computations are only repeated if their inputs change. May be combined with lazy evaluation. Lambda calculus, lazy initialization, look-ahead, short-circuit evaluation, non-strict programming language, normal order evaluation, notes. References: Hudig, Paul. Conception, Evolution, and Application of Functional Programming Languages. ACM Computing Surveys 21, 383 385 Reynolds, John C. Theories of Programming Languages. Cambridge University Press. ISBN A9780521594141. Further reading, Wadsworth, Christopher P. Semantics and Pragmatics of the Lambda Calculus. A PhD thesis, Oxford University, Henderson, Peter. Morris, James H. A Lazy Evaluator. Conference record of the third ACM Symposium on Principles of Programming Languages. Friedman, D.P. Wise, David S. S. Michelson and R. Milner, ed. Comms should not evaluate its arguments. Automata Languages and Programming. Third International Colloquium. Launchbury, John. A Natural Semantics for Lazy Evaluation. Proceedings of the 20th ACM Sigplin Sigict Symposium on Principles of Programming Languages. doi, 10.1145/158511.158618. Design Patterns, John Hughes. Why Functional Programming Matters. The Computer Journal, Special Issue on Lazy Functional Programming. Volume 32 Issue 2, April 1989. Philip Wadler. How to Replace Failure by a List of Successes. A Method for Exception Handling, Backtracking, and Pattern Matching in Lazy Functional Languages. Functional Programming Languages and Computer Architecture. Lecture Notes in Computer Science, 1985, Volume 201/1985, 113-128. Laziness in Strict Languages, Philip Wadler, Walid Taha, and David McQueen. How to Add Laziness to a Strict Language, Without Even Being Odd. Workshop on Standard Mill, Baltimore, September 1998. Blog posts by computer scientists, Robert Harper. The Point of Laziness, Lennart Augustsson. More Points for Lazy Evaluation, External Links, Lazy Evaluation at the Portland Pattern Repository, Lazy Evaluation at Haskell Wiki, Functional Programming in Python becomes lazy, Lazy Function Argument Evaluation in the D language, Lazy Evaluation Macros in MAL, Lazy Programming and Lazy Evaluation in Scheme, Lambda Calculus and Boost Libraries in C++ language, Lazy Evaluation in Perl.